Hey folks, for this screencast, what we're going to do is we're going to take my RC aircraft series that I've been putting together and basically take this derivation that I did by hand here on the whiteboard and convert it into some software and some MATLAB code. So I brought some of the parameters in here now, but I haven't completely put it in here. Basically what I'm looking at is going through the steps. So the first step is choosing a wing cube loading, and if you remember, I was choosing this here, the aerobatic or sport aircraft, which was between 7 and 10, and so I chose a wing cube loading of about 9. I then made this table over here where I estimated all the weights and added them all together, and then computed the servo, the battery, the ESC, the motor, the prop, the receiver, all these things, and then I basically have this function here where I just add everything together. Now when you build your aircraft, you're going to change this and you're going to look up these weights online, but before you get your final weight, and I was getting a weight of about 40, estimate of about 40 ounces. Okay, and so there was my weight estimate. Once you have a weight estimate, you kind of need to decide what sort of thrust to weight ratio you want. Now when you pick your motor and your prop and your battery and your ESC even, this is kind of like your power supply and propulsion system, and that kind of dictates how much thrust you're going to get. And so based on all of these things, you can kind of know what your thrust is. And so it's possible what you can do is you can say, like, I want to pick my thrust to weight ratio and then multiply that by your weight to get thrust. But it really depends on the way you look at it. So I'm going to say one design point is to pick a motor and figure out its thrust. And in the video here, let's see, my body is in the way. Let me see if I rewind it. There we go. Oh, my shadow's in the way. Okay, I'll pause it and come back. Okay, folks, so it turns out that my thrust was 33 ounces, okay? And so, again, if you choose the thrust value, you can then compute the thrust to weight ratio, which is this thrust divided, and let me put thrust in here and do thrust divided by weight like this. And then I'm going to throw a return in here, and you basically say, okay, weight was capital. You can basically say here, okay, there's my thrust to weight ratio of 82%. If that thrust to weight ratio is high enough for you, then you can move on. Now, where did I get this thrust from? Well, this thrust comes from thrust tables online, given the power supply, propulsion, and the battery ESC motor combination. Now, the other design point, what you can do is you can say, well, I want a thrust to weight ratio of 80%. What thrust do I need? And then so you can take your thrust to weight ratio and multiply that by weight, and then you can come in, I need to put the return statement. There's a lot of other stuff in this code here, and I'm going to go through it line by line, but I'm just putting returns in here so I can kind of talk about it. So this means if I want a thrust to weight ratio of 80%, I need a thrust of 32 ounces. So if I kind of estimate the weight and then go on and then compute with my thrust to weight ratio and then say, okay, I need 32 ounces of thrust, I can then go online and pick a prop motor ESC battery combo that gives me that much thrust. I can also sort of do a redesign, because once I know how much thrust I need, I can go online and find it, which means I can get the weight of that component, and then I can put it in the computer, and I can iterate on those a couple more times. The same thing with this fuselage too, right? I estimated the weight of the fuselage based on some rudimentary calculations with some balsa and some basic lengths and stuff. Once I actually build the airframe, I can weigh it, and I can get a better weight, and I can go back in this program and see if my numbers are still good. So you can kind of use this to your advantage to kind of choose what you want to do. So this is another design point where you select the thrust to weight ratio. Now I'm going to go with the first one where I pick the thrust, and then I make sure that my thrust to weight ratio is high enough, because I was the one who actually went out and found these components. Okay, so then at that point I can get rid of this. Yeah, see, from here on you can go online and find a motor that provides enough thrust. Then you can compute the weight more accurately given the motor battery rate. All right, so now what can we compute? So if you remember in the video, what you do after this is you compute the area of the aircraft, right? So remember that wing cube loading is weight divided by s to the 2/3. And so what you can do is you can say s is equal to the weight of the aircraft divided by the wing cube loading from the first part, and then that is raised to the 3/2 power, and that should be around 2.7. So let's see if that's right. 9.37. This is ounces. Weight is in ounces. 40 ounces. Did I do this math wrong? Weight divided by wing cube loading was 9. Give me 1 second. Okay, I went back and looked at the equation. It's actually weight divided by s to the 3/2. So I just had to transpose these two numbers. And so then I got 2.7, and that's in square feet. Okay? Once you have s in square feet, you can now pick an aspect ratio. And so these numbers are from a different aircraft. So if I remember correctly from the video, okay, folks, I moved inside. It was getting kind of hot. Anyway, so you choose the area, you compute the area, and then we choose the aspect ratio. So I had my aircraft was kind of a small aspect ratio wing at 4.5. Now I could have made that a little bit bigger to make a glider, but the longer you make the aspect ratio, a lot harder it is to build it, just because you're really starting to get long, thin wings. So I did 4.5. If you use a rectangular wing, then you can use this equation to compute wingspan. And this is going to be in feet, so I'm going to multiply by 12 to get to inches. And then you do s divided by, let me not do that, okay. So that's going to be b in feet, and then you're going to do s divided by b to get c. And then I guess at that point we can return, and so I've got a wingspan of 3.5 feet, which is pretty good, and a chord of 0.78. So if I do that times 12, yeah, that's about 9.36 inches. Yeah, that seems pretty good. When I finally build this, I'll probably make it a little bit different sizes, but anyway. So at this point, then we can do some, it looks like I'm doing some flight speed regimes. If I go, oh gosh. If I go back to my video that I was looking for, let's see, how to design the aircraft wing. And the next step is to actually get the airfoil. And so let's see if that's actually in this code here. It looks like, the reason why I'm computing this is because in order to put this in XFlyer, I need a Mach number. And so I'm assuming that I'm flying between 5 to 20 feet per second, which is fine. I need my altitude is I don't need altitude. I need my density at altitude. And I'm assuming I'm flying at sea level because I live close to the beach. Here's mu. I guess you can Google that. What is that? Kinematic viscosity. Let's see. Yeah, there's 1.88 E minus 5, but that is in kilogram. This is in the wrong units. And this is also, so this is difficult. This is kilogram per meter cubed, and all of this is in feet and ounces. So, when we compute a Reynolds number, we need to be a little bit careful, right? We need to, I guess this is going to be in meters per second, 5 to 20. Rho is going to be 1.225. This is mu in SI units. So you're going to have rho, V, and then CSI. So I'm going to do CSI. So that's in feet, right? 0.78 in feet. So if I do C, is it divided by 3.28 to get to meters? So that's C in meters. And then divided by mu. That will give us a vector of Reynolds number. Our Mach number is going to be speed of sound divided by, V over A infinity. And then it looks like I'm creating a matrix for XFlyer. I'd like to plot this. So let's do figure plot V comma M, and then figure plot V comma Reynolds number, and then return. Okay, so this is probably Reynolds number. This is Mach number, yeah. So this is my flight regime. So if I go into XFlyer and pick a Reynolds, a Mach number of like 0.05 or 0.04, that's probably fine. And then it looks like I can pick a Reynolds number of, 2.0 times 10 to the 5th. So that seems pretty good. Okay, so then my design point is going to be Mach number for, what is that, XFlyer 5 is going to be M equals 0.05, and then I'm going to do Mach number and Reynolds number. Reynolds number is going to be 2.0 E5. And I think that's 2 million. I don't want to do the math out. No, that's only 200,000. That's actually, okay, yeah, these are smaller aircraft. So it'll be 200,000, 200,000. So in my YouTube videos, right, there's one on here. If I go to playlists and I go to RC aircraft design, in here there's getting lift, curves, slopes, and drag polos using XFlyer 5. And if you scroll through this video, at some point here, see, I choose the Reynolds number and I choose the Mach number. So go back and watch this video, and you'll end up getting what we're essentially trying to get, which is, let's see, these lift, curve, slopes. Yep, these ones here. So these are for different airfoils. So here, oh, it hasn't paused. So this is lift versus angle of attack. You've got pitch moment. You've got lift to drag ratio. You've got your drag polar over here. These are the variables that you're trying to get for your airfoil. So at this point, I'm going to say, yeah, pick an airfoil. So I'm not going to pick this. Assume Reynolds number is 50,000 to 300,000. That's a pretty good range. And then it looks like, pick out all of these values from XFlyer 5. So this is your zero lift angle of attack. And so if you look here, right, when this red line crosses the x-axis, it's, according to this is probably a different airfoil. So let's just do this one so you guys can get it. Let's maximize this screen, and let's see for this red. So this is an N9.0. Yeah, it's an N10. I wonder if we can go back to where I actually put these airfoils in. Yeah, there we go. There we go. So it looks like in blue here, that is the N10. So it looks like this kind of like supercritical airfoil or something like that. It's pretty cambered. That's the N10. And then we kind of skip ahead in the video to where we actually created the plots. And it's weird that they changed the color scheme. Like red is now N10. But anyway, so the zero lift angle of attack is like -5. So let's plug in -5.0 pi over 180. And then in degrees, I don't know why I did that. Okay, whatever. And then the A0, this is CLA. This is the lift, curve, slope. Okay, and what we can do is we can just take 2 points on a line. So we can take rise over run. So I'm going to take the easiest one. So 0.6 over. So when angle of attack is 0, it looks like I've got an angle of a lift coefficient of 0.6. So I'm going to say that my delta lift coefficient is 0.6 divided by 5 degrees. So I'm going to say alpha 0. Okay, so that's my lift curve slope. And I'm going to do a return because I want to make sure that that number makes sense. So I'm going to do, see, that doesn't make sense at all because it should be a positive number. And the reason why it's negative is obviously because alpha 0 is negative. So I just need to throw a negative sign on this guy here. And then I get 6.88, which is pretty high for a wing, but for an airfoil, it's actually pretty standard to be that high. Now, what we need to do then is we need to use this aspect ratio equation where we find the lift curve slope of the wing. So this is sort of the efficiency of the wing, and 90% is usually a pretty good ballpark. And then what we can do is we can compute C capital LA, which is the lift coefficient slope, lift curve slope of the wing. And it's using this equation here, pi EAR. And this is where having a big aspect ratio helps, because as this number gets bigger, this number gets bigger. And so we should be able to do compute CLA and then type in return so that we get C 4.46. That's a much more realistic number for a wing. And then we can compute CLA in degrees, and that's CLA times pi over 180. We're not going to output that. At this point, we can find lift curve, lift coefficient versus angle of attack. So we're going to go minus 15 to 15, 100 data points. And then we're going to go, the lift coefficient is CLA degrees times that. So this is the equation for lift coefficient. It's the lift curve slope times angle of attack, the actual vector, minus the zero lift angle of attack. And then we can create this plot here. And so hopefully we should see figure 3. Booyah. So there's figure 3. So at a lift coefficient, or sorry, an angle of attack of -5, I thought it was -6. -5, I'm sorry. We have a lift coefficient of 0, which makes sense, right? So if our angle of attack is 0, so if our aircraft is just flying steady and level, our wing is cambered, and so we're going to get a lift coefficient of 0.37. Okay, that sounds good. I'm confused at the lift. Oh, okay, it's 0.6 when it is when it's 0, right? What's CLA? It's 6.88 per degree. So CLA times 0 minus 5 times pi over 180. Minus is a plus. So yeah, you get 0.6. And then if you do 0.6 divided by 1 plus 0.6 over pi times 0.9 times 4.5, you get 0.57. And is that what I get for the lift coefficient at 0? No, see, I got 0.37 or 0.4. So why was the aspect ratio not 4.5? It's 4.5. So what did I get for CLA? CLA was 4.46, right? So if I do 4.46 times 5 times pi over 180, I get 0.39. Interesting. So it must this curve here must shift some things around. I guess I've never investigated that. So it doesn't necessarily just shift the whole curve. It looks like it changes the slope. So that's what it does. So it keeps the anchor point the same at -5, but it changes the whole slope. So you'll still have the same 0 lift angle of attack, but at 0 degrees you're going to have less lift. Okay, that makes sense, right? Okay, so we've plotted lift versus angle of attack, and now we can compute angle of attack as a function of velocity. Okay, so this is an interesting thing, right? So as I'm flying, I need lift to equal weight, right? And so if I am flying slowly, I'm not going to have a lot of lift, so I need to increase angle of attack to increase lift. And so basically the equation is lift equals weight, which equals 0.5 times rho times v squared times s times CL, right? And so I'm going to do this in steps. First, I'm going to compute the lift coefficient, which is 2 times the weight, because there's a 1/2, divided by rho times v squared times s. And that's going to give me lift coefficient. Now we have to be careful with our units here, right? So rho, I'm going to do 0.238. Oh, I think it's 0.0238. Let's do density at sea level in slugs per foot cubed. It is 0.002378. I was close. 0.002378. So this is rho. Let's go back up here and change this to rho SI, and this to rho SI. And I'm going to do VSI here and change this to VSI. And then M is VSI. I think I got it. This is mu. I don't need mu anywhere else. And I got to change this to VSI. VSI. Okay. So there's my rho in English. And so CL, I'm going to say required, is 2 times the weight, but that's in ounces. So I need weight in pounds. Ounces per pound. It's 16, isn't it? Yeah, it's 16. So weight in pound force. So weight in pound force is weight divided by 16. So if I take my weight of 40 ounces divided by 16, I should get 2.5 pounds. So there's my weight in pounds. I'm going to move that up here so I have it all together. Okay, so there's weight in pounds. And then I'm going to grab a rho and put that up here so it's all together. This is slugs per foot cubed. Okay. And then that is going to be divided by rho times V squared. And I need to do the dot times because it's a vector, times S. Okay, and that's going to give me CL required. Now V, I need to compute V is VSI, so that's meters per second times 3.28, and that'll give me feet per second. Okay, so hopefully this is going to give us realistic numbers because we are going to do a figure and we are going to plot V comma CL required. And I'm going to comment this out real quick. And let's see, so that's going to be not figure 1. I need to label my axes. Figure 3, figure 4. Did it pop up? Is there a figure 4? X label, velocity in feet per second. And then Y label is, oh, there's a return up here. It didn't even get here. And then Y label is CL. I'm going to say lift equals weight. Okay. Oh, matrix dimensions must agree. Oh, I got to do a dot divide. Divide by the vector. And so one of these is going to tell me, here's CL required. Nope, that's angle of attack. There we go. That makes sense. So at, 5 meters per second is, yeah, I guess that makes sense. So yeah, so for this aircraft, if I'm flying at 20 feet per second, I need a lift coefficient of 2, right? That's a lot of lift. So this aircraft weighs, it seems like it weighs a lot. Like there's this thing, it weighs a lot and there's not a lot of wing area, right? So I need to be flying really fast. My thrust to weight ratio is 0.8, so I might need to throw some landing gear on this thing to, like, I don't know if I'm going to be able to hand launch this aircraft. It's also possible I overestimated the weight, and once I build it, that won't actually happen. So now once we have the lift coefficient, let's compute the angle of attack. So the angle of attack required is, if you remember from this equation, you just take your CL required divided by your CLA degree, and that will give you alpha minus alpha 0. So then you just need to add on alpha 0 degree, and alpha required, I'm just going to do degree. And then we can just copy this here and then do V comma AOA required degree, and then change X label Y label to AOA in degrees. And then do I have a return? Cool. So then this should be my 5th figure. There we go. So yeah, so this is preposterous. Well, I say preposterous. Once you go above about 12 degrees, you really aren't going to do that well. So I'm saying that my stall speed is probably, actually I'm only doing like 100 data points. Let me get 1,000 data points for alpha. Oh wait, I need to do velocity. Where's velocity? 5 to 20. Let's do linspace 520 100, because that was only like 15 data points. Let's see. There we go. Okay, so now this is a lot smoother. So yeah, so here like 8 degrees, so that's like 27 feet per second. So I'm saying my aircraft probably is not going to take off, because once I hit like 12 degrees, my vehicle is going to stall. So I'm going to say I need to hit like 26 feet per second before I can take off. So 26 divided by 3.28, oops, is 8 meters per second. And how do you convert to miles per hour? So there's 5,280 feet in a mile. And then, why did I get 0? Oh, okay, I'm doing format bank. Times 3,600. So that's like 17 miles an hour. So yeah, I mean, I'm gonna have to like put landing gear on this thing and really cook it down the runway. Or what I'm hoping is that my weight is just completely wrong. So I did the wing cube loading of 9, and I got a weight of 40 ounces. But imagine if I did 30. Let's see how that changes my vehicle. Now, you see, this is what's nice about this program is I can do like a redesign. So now let's see where that 12, see now look at that. See my 12 degree, if I want to do the same, yeah, see there's like 10 degrees. See now I'm at 24 feet per second. And so I guess that didn't really change much. 26 to 24, 3,600. Okay, 16 miles an hour. So, I mean, I don't know how hard I can throw, you know, but I could probably throw it like, 10 miles an hour. And, or I could just get more thrust. Well, that's the thing. If you have more thrust, it doesn't really matter how fast you take off, because you don't need any lift when you take off. The problem here is that because my thrust to weight ratio is less than 1, like I need to have airspeed. And that's actually another thing to consider, that if I take off with the aircraft like this, maybe I don't have enough thrust to overcome weight, but if I'm flying and I have a little bit of lift and some thrust from a high angle of attack, I still might be able to pull out of that. So there's some trade-offs there. Anyway, the whole point of this code is to use this as sort of a design tool. So let's keep going. So we've got our angle of attack. Let's get rid of this. So for a given flight speed, how much thrust do we need? Okay, so let's plot drag. So if you look in the video, you have this sort of drag polar, okay? And you can kind of grab your 0 lift. So that's 0.15, 2.5, yeah, so it looks like I got CD 0.01. This is a drag coefficient at 0 lift. Let me get rid of this return. CD fit is 0.037. Not entirely sure what that is. I'm gonna get rid of this, get rid of this, get rid of this, get rid of all of this. Now let's compute the wing drag coefficients. So that's fine, but we also need to do the same for CD. I don't want to call this CD fit. I want to call this CD2. It's the quadratic component. So this is CD naught, and then this is CD2, 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 and then we can compute CD. So we got CD naught plus CD2 times alpha. What is it? Is it alpha degree? No, not degree. Alpha 0. No. There it is. So there's the vector. Do I have I don't have a radian version. So I'm going to do alpha is alpha degree times 180 over pi. No. Pi over 180. Okay, so then that will give me CD is CD naught plus CD2 times alpha dot half squared. And then I can plot V, comma CD, and X label is velocity in feet per second, and then this is CD. Okay, let's see what that does. Vectors must be the same length. Oh, okay, it's because what I need to do is I need to plot angle of attack. So I need to do alpha AOA in degrees and do alpha degree. Okay, And then, yeah, CD1 there. So there's my drag, there's my quadratic. So at 0 degrees angle of attack, I've got 0.01, and then as I increase there, I go from there. Now, this is the really hard part about drag. This is only wing drag. You probably need to add in some fuselage drag here, right? And increase this. So basically what I've done here is I've like shifted the drag polar up. And this is why drag is just like really, really difficult. It's used to compute maximum speed. My recommendation really would be to put the entire aircraft into like a SolidWorks program or something like that, or like a 3D modeler, and see if you can get the drag coefficient of the entire aircraft with the wing and the fuselage and the tail. Because this is just like a really hard parameter to get. I'm gonna say that you're just gonna add a parameter called CDF down here, CDF for fuselage drag, and I'm going to just call this fuselage drag, and I'm just going to add it to this equation here, CDF, and I'm going to say get this from another program, okay? And again, that's just kind of a hard parameter to estimate. So once you do that, what you can do is you can vary the flight speed here, 1/2 rho v squared SCD. And so I'm going to vary the flight speed from 5 to 20. We've already done that. And so I'm just going to, oh, I see what I'm doing here. So the thing is that you need to compute, this is drag per angle of attack. What you want to do is compute drag at a specific flight regime. And so what you want to do is you want to say D, so drag is 0.5 times rho in English, right? Times V dot hat squared times S. And then you can't do CD. You have to do CD0 plus CD2 times alpha required. So there's AOA required in degrees. So I'm going to do AOA required just in radians. And that's going to be AOA required degree times 180 over, no, pi over 180. And so that's going to give us the angle of attack required as a function of flight speed. And so I can come down here and say AOA required dot half squared plus CDF. And then that will give me drag. And then that's also, by the way, going to give me thrust required, which is what I want. And then I can plot velocity as a function of thrust required. And I'm pretty sure this is in pound force. So I'm going to do times 16 to get to ounces. And this is going to be in feet per second. And this is going to be in thrust in ounces. And I'm hoping, now let's compute the drag coefficient. I don't need that. Let's compute the total drag. I don't need that. I don't know what I was doing here with this other code. Lift to drag ratio, that's just kind of extra thing. Empennage stuff. Okay, yeah, we'll get there in a moment. All right, so let's see if we if this is good. So let's see. So there's AOA as a function of velocity. I don't know what figure 6 is. CD. Why is my why doesn't, oh, there's 2 returns. There is a figure in here somewhere that is like not actually being used to plot. There it is. Okay. That's why I was making a blank plot. Blast. What line of code? Line 140. It was this one. Oh, okay. It's because V is a vector and angle of attack required is a vector. So I have to do the dot times operator. Okay, let's see. Figure 1, figure 2, figure 3, figure 4, figure 5, figure 6. And then there we go. Sweet. So according to this, at 33 ounces, by the way, assuming a fuselage drag coefficient of 0.2, which I completely pulled that out of nowhere, we're going to fly around 54 feet per second. Now, keep in mind, this does not include the efficiency of the prop, right? As you fly faster, the prop is not going to create as much thrust. So this is like very, very unrealistic parameters. Ah, I did it again. I'm sorry. Sorry about the inception. Ah! Okay, so 53 feet per second times 3,600 over 5,280, 36 miles an hour. Yeah, I mean, that actually seems right. If we got rid of the fuselage drag, how fast does it say we can go? See, that's what's ridiculous. Like if you just do, that's why flying wings are so efficient. I mean, you can scream this thing. You only need 2 ounces of thrust to fly, according to this. That's ridiculous. Anyway, all right, clear CLC, close all. Let's add that fuselage drag back in there. So now it looks like the rest of the code is sizing the empennage. So I usually assume like the empennage is going to be 50% of the wingspan. I assume the aspect ratio of the tail is the same as the wing. Here's the area of the tail, the chord of the tail. And then you have to compute the center of mass based on weight of the components. Did I talk about this in my video? Like did I talk about like the stability and the aerodynamic center and things like that? I guess I didn't. So you have to keep in mind that here, let me get rid of, I'm losing my train of thought. Let's get rid of this stall speed here because you can get that from that last chart. I hope I talked about this in my last video, but basically you need to make sure that the center of mass is in front of the quarter chord of the wing. And so what you can do is you can compute the aerodynamic center, which is the chord of the wing over 4. And then if you use the main wing, if you use the main wing as the reference point, you can use the center of mass formula to compute the center of mass of the vehicle. Or if you just build it, you can ensure that the center of mass is not behind this. So according to this, oh, I put a return again. So see, like if my wing is 0.78 feet, right? My quarter chord is 0.19. So I need to make sure that my center of mass is in front of there. Now, typically what people do is, yeah, the tail is like weighs a lot and it sort of makes it sort of tail heavy. They put the battery and the motor and the prop in the front, which are like heavy components, and that sort of shifts the CG forward. And so when you build your aircraft, you just need to make sure that it's like lined up properly. But what you can do is, you can grab all of these and you can say like, the weight of the servo is this, but where is it in reference to the CG? And so you can kind of say like, it's 2 inches behind the CG. And then the battery, I'm going to put it 2 inches in front, of the leading edge. So this is in reference to the leading edge of the main wing. And so the battery location, I'm going to say is 2 inches in front. The ESC, I'm also going to say is 2 inches in front. The motor, on the other hand, I'm going to probably put that 4 inches in front. And then the prop, obviously, is going to be same. The receiver, I'm going to try to put that's prop. And that's motor. And then receiver, I'm going to probably say that's just right on the quarter chord. The fuselage, this is going to be a hard one. This one, the control horns and stuff, I'm just going to say is 0. The fuselage is difficult. My recommendation is you build the fuselage. This fuselage is probably going to be tail heavy, so it's probably going to be like 10 inches behind the quarter chord, if I had to be honest. So then basically what you do is you take all of those things, right, and you use the center of mass formula. So XCG is weight of the servo times X of the servo, weight of the battery times X of the battery, weight of the ESC times X of the ESC, weight of the motor times X of the motor, and then weight of the prop times X of the prop, and then weight of the receiver times x of the receiver, and then weight of the control horns and rods, x of the control horns and rods, plus weight of the fuselage times x of the fuselage. So again, this is the location of the CG of a particular component, and then divide it by the total weight, and that is going to give you the CG in feet. And we got 3 inches. 3 feet. Oh, crap. These are all in inches. Okay. What do I want to do here? I just need to take this and divide this by 12. There we go. So according to this, if I built this component the way I had it, the CG is 0.25 feet behind the leading edge of the wing, and the aerodynamic center is 0.19 feet behind the leading edge of the wing. So this is unstable. So what I can do is I can compute what's called the static margin, which is xCG minus xAC divided by the chord length. And if this value is positive, it means I am unstable. You need to have a negative stability margin. So what can I do? Well, I can try and shift the battery forward, right? So the battery is at 2 inches. Maybe I can get it 3 inches in front. And now, see, it still wasn't enough. Let's see. So the fuselage is 10 inches. Maybe I need to, like, you know, shorten the tail, you know, and make this like 8, because the fuselage weighs a lot. Boom, there you go. So I fictitiously shortened the tail so that the CG of the fuselage was not as far behind the leading edge of the wing. And then now I've got a stability margin that's negative. You can see the CG is in front of the aerodynamic center. Okay, so this code is on my GitHub, MATLAB Aircraft Seminar Series RC Aircraft Design. This is a good tool that you can use to sort of size your aircraft and things like that. There's a lot of bells and whistles in this, like you know, estimating all of your weights, finding the motors online, making sure your units are correct, you know, picking a wing cube loading, picking an aspect ratio, estimating the fuselage, which is very difficult. You can't really do that until you build it. You know, choosing the motor depends on your thrust and your weight and your thrust to weight ratio that you want, and the components that you can all find and get together, like battery and ESC and things like that. And then you also have this sort of, you know, elephant in the room, which is the drag of the fuselage, which is also hard to get, and sometimes you can get it from another program. I've seen some people use SolidWorks or even DATCOM programs to get, like, you know, 3D drag. But yeah, I hope you can use this to your advantage to create an aircraft and go build something. I'm going to try to build this aircraft that I've designed here and tweak the numbers and make them a little better and go from there. It probably won't be anytime soon because of the pandemic, but hey, hopefully you can use this code to your advantage. And like I said, you can download this on my GitHub, and I hope you enjoyed this video, and I'll talk to you all later.